All right. Well, welcome back. Good to see you guys again. I didn't get as far as I had hoped to or planned to on Tuesday, so let's make sure we wrap things up here today. As you know, on Tuesday, just to kind of recap, we passed back the thermodynamics test, and we kind of went through all those problems. And then in the second half, we got started here with our first chapter on optics. And the point or the idea of this first chapter on optics was really controlling the light. And we looked at reflection. And so I'll turn this back on and say, all right, one way to control the light is to take, say, a laser beam. And so here's kind of this laser beam again. And then this mirror. And say, all right, what happens when the laser beam hits the mirror? Okay, it reflects. And so what direction is it going now compared to what direction did it go before? And so what we did is we said there would be an incident angle and a refracted angle. We called that theta 1, and we argued then that the reflected angle would be the same as the incident angle, the law of reflection. Now let me not spend too much time there, because the second piece of this puzzle was here. The second way of controlling light, and the second main point in this chapter, is refraction. And so if I replace this nice little diagram here, hopefully you will see that as the light beam comes in and hits the glass, and so maybe I'll just do a little outline of my box of glass here. I will draw a surface or a normal perpendicular to the surface. Let's call that theta 1. And where we left off was this. If you kind of mark right here and right here, then the beam is currently going in that direction. But in order to get there, that means through this glass block, it had to go this way. If we draw the normal on down, and the direction of that ray is going, and I'll call that theta 2, I wanted you to see both last time and then kind of as a review here as we got started, notice that as the light came in, it shifted in its direction. It changed. There was a turning to it as it went into the glass. You probably also noticed there's a turning to it when it goes out of the glass. And of course, once we understand one, we'll also understand the other. But when the light is going in, there's a turning. And so theta 1 should be related to theta 2. And so I ran short on time there, but I wanted to derive what is called Snell's law. And those 2/3 of you that have already done the lab this week, and the other third of you that will do it this afternoon, will notice that that's what the lab is on. It's on Snell's law, and you're supposed to then discover here Snell's law. So let's derive it here real quick. Yeah.
Those two lasers going in and coming out will be parallel?
Oh, yeah. In this case, the answer is yes. It's a good question here. If I draw, and I'll change colors here, but if I draw this beam, that's where the beam is going to go without anything in the way, right? Then when I put my glass block on here, and I don't know, is it dark enough? Can you see the beam? I could hesitate to turn more lights off. Well, that's not too bad. Yeah, that's actually real good. But when you see it in this case, you will see that they are parallel. And the reason they are parallel is because the edges of my glass block are parallel. And you actually have a homework problem to show that if those two sides are parallel, there'll be a bending to that light coming in, there'll be a bending to the light going out. The overall effect on that beam of light is that it will have a lateral shift, and you're asked in the homework to calculate that lateral shift. In the lab, you are asked to measure the lateral shift, but it is parallel, yeah, so, yeah. And you're like I said, in the homework you're asked to prove it. If we have time, maybe we'll actually prove it ourselves here. But again, what I want you to see here, and maybe I'll take that off and just turn the chalkboard lights on here, but I want you to see the labeling that I've done. I have called this the incident angle theta 1. This then is I'm going to call the refracted angle theta 2. What angle is that? How is theta 2 related to theta 1? And that's the part that the second half of this lab is. So the point is we can control light either by reflection. And so I'm sure you're used to mirrors, and that's what the next chapter is all about, making mirrors. Mirrors that are flat or curved, they either magnify things or they make them smaller. Or we can control the light by making them go through a refracting surface, like glasses or lenses on a camera. Either way, the light is controlled. So that's why this first chapter on optics is the basic workings of how can we control the light. A, reflection, B, refraction. All right? And so I claim that these two angles are related. But how are they related? Well, that was discovered by Snell's. Let's run through his logic here real quick. Here's the part where I kind of got sidetracked on the last lecture. I was asking about the speed of light. Because as we will hopefully see in a minute, the whole reason light bends is the same reason anything bends or turns, a difference in speed. And so you might remember these little wheels that I had, and we'll come back to them in just a second here. Well, might as well turn on the classroom lights too for a moment. All right, so let's go back to the speed of light. When I asked you what was the speed of light, you said? Okay, symbol C, 3 times 10 to the 8th meters per second. But I wanted to make sure we were a little more clear. This is the speed of light where? All right, so with no other molecules around, in a vacuum. Because I think we say that too quickly. Oh, the speed of light. Oh, the speed of light. Oh, the speed of light. Like it's always the same number. Not true. The speed of light does change as it goes into some materials. And so what we're going to do is write it this way. The speed of light is c, the fastest it will ever be, divided by an index. This index will be used to label how much has the light slowed down. This is called the index of refraction. I personally like the less common name, index of speed, because it is really telling me how much has the light slowed down. And how much it slows down is going to tell me how much does the light refract. And hence that's why the more common name is what is the index of refraction. And so I thought I would start here today by pulling up this table. It's table 1 in your book. It's one you're going to get used to, and you're going to have to keep flipping back through, not only in this chapter, but the next 3 chapters as we go through our optics. And we will have light going into different material. Let's start with the simplest material, air. If the light is in a vacuum, and let's say outer space is about as close as we're going to get to a vacuum. I know there's a few molecules every so often, but let's just say there's absolutely no molecules. Light would be coming in at this speed, 3 times 10 to the 8th. But then, as it hits the atmosphere, as it goes through the air, it's going to interact with molecules. Now, air doesn't have a whole lot of molecules. They're kind of spread out compared to, say, water, or compared to, say, glass. So you would expect there to be some interaction, but not too much of an interaction. And that interaction will slow it down. By how much? Well, look at the number for n. What is this number? 1.000293. And what we mean by that is it has slowed down just a small fraction. In other words, n in a vacuum would be what? Yeah, do you see how it would be 1? That would be the place where we would go the fastest. Light is going to go the fastest through our vacuum. But all of a sudden now, we get into air, and our speed has been reduced. I will just round it to a 3 there. 0.0003. Not by much. And in fact, don't be surprised as you do the homework, or as I do examples for you, when we have a situation like this, and I put a glass block up here, and I say, okay, it starts in air and goes into glass, I'll probably just say the speed is the speed of light. The index is 1. And just not even worry about that last set of significant figures, unless it's important. And there will be a couple of experiments. In fact, I got one example today that hopefully we'll get to where it is going to be important that we include that 4th decimal place. So then we would have to include it. But if we're only interested in 2 or 3 decimal places, then we just say the speed of light in air is basically the same as the speed of light in a vacuum, and there's very little effect. But you can see that that's not true for all materials here. As we go from air and say go into something a little thicker here, how about through water? Look what it says there. 1.33. And so there, the light has slowed down by 33%. Yeah.
Is it just a coincidence that that's such a nice fraction? 4/3?
Oh, 4/3? Yeah, I think it's just a coincidence. Actually, yeah. But it, yeah, is it 3? At least to 3 decimal places, it's a 4/3. I doubt if it's exactly a 4/3. In fact, you'll see in a minute something else here too. So it's not exactly even that number, but more details as we go on. And again, let me just put a couple of them on here. They got glass in here anywhere? Where? Oh, okay, here's some crown glass and some flint glass. Let's do the crown glass here. And so another one that we'll use a lot is our glass. Our glass will be around 1.5. So again, the light does slow a little bit. They got 5.2. There's different kinds of glass, so I'm just going to give a general number. And there could be a whole range of indices. And in fact, that is the experiment for those of you who did it, and those of you who are about to do it this afternoon. That's what you'll be asked to do, is define the index of our glass block. And you put this little block out there and you find the index. In fact, our block is more acrylic. Do they have acrylic up there? Okay. Not sure. I don't think so. But yeah, I don't think so. Well, but anyways, like I said, this is this big chart, and then you can kind of see the pattern there. That, of course, it would depend on the molecules. But let me add one more in here that we'll see in about a half hour. This is slowed down because the light is interacting with the molecules. So you would expect it to be different for different materials, right? It's different for water, it's different for glass. But also, wouldn't you expect it to be a little different with different frequencies? Because it's how it's interacting with the molecules. And there is a slight variation to this index depending on what frequencies we have. And so, more on this in just a second, but this is a very general number. There is small variations as we go from different wavelengths. Well, like I said, the reason I wanted to put this up here is because then I wanted to show you this little animation here. All right, let's take a look at I lost it. Ah, there it is. This animation here. And so here is the idea of light, starting here at index 1, so let's just say that's air, and then we are shining it into a block of glass. Now you can hopefully see that it's going straight in.
The N for acrylic is 1.49.
Oh, okay, good. Okay. Okay, 4.9. Actually, that's really good, 4.9, because a lot of people got 4.9 yesterday in lab. That was, okay, good. So you guys in today's lab, that's hopefully what we'll get, a 4.9. Now, back to this picture here. I'll set it up with my laser beam. And so that picture looks something like, and maybe I'll shut the chalkboard off here for a moment here. But there is that picture. Now, unfortunately, you can't really see the individual wavelengths like you can in this animation. That's why I like the animation a little bit better. But I'm hoping you see something here. I'm hoping you see the consequence, because there are two consequences I want you to see. If the light is going to change its speed, if it is going to go from a fast speed to a slow speed, or slow to fast, but we'll just talk about fast to slow here. What do you notice first right away? What do you notice here? Can you tell anything between here and here? And these little wavelengths, these are supposed to be the crests of the wave. See what happens when the top of the wave enters into the glass right here? See how the wave behind it is still out here going faster? And so as this wave comes in, as the crest comes in, then the one behind it actually kind of gains on it for just a moment. I mean, it only gains during the transition, right? And because look what happened once it's inside the glass. What do you notice there? Yeah, the separation between them is exactly the same. So the point here is that when you change your speed, the wavelength is going to change. Now, in this area, does the wavelength change? No. In this area, does the wavelength change? No. Where is the change occurring? Right there at the border, the transition. While one is going slow and the other is going fast and catching up to it. And so we should probably ask ourselves, what is the mathematical relationship between the wavelength inside the glass compared to the wavelength outside the glass? Yeah?
Well, I was going to say, are we going to see different colors inside that medium?
Oh, the whole question about color comes into play. Let's see if I can answer that two ways. I'll start with this one. You would never see a color until the light went into your eyes.
Which would be outside of the medium.
Which would be outside of the medium.
Okay, but if I was inside, would you see?
Okay, so, okay, see, I think you get my point here. That if this goes, like here, if this beam of light goes through this glass block, as we're going to see, its wavelength gets smaller. I prefer to say its wavelength got smaller and just avoid the whole question, did the color change? Because when it comes out of the glass block and goes to your eyes, what happens? It's going to speed up when it goes back into the air. Then it's going to go into your eyes and it's going to get smaller again because of the salt water. And so I don't care where you are. You could be underwater. You could be in the glass, you could be in this room, but eventually the light that you see is in your eyeball. And regardless of what it is, it's always going to look the same color to you. So that's probably the best answer I can give you. The second one is, you would call color, based upon wavelength, then is probably not a good idea. It's probably better to connect it to its frequency, because as we're going to see, its frequency is still the same. And so then I should just say, no, it has the same, quote, color, but I will do one thing different. I won't even, you'll see it here all the way through science. We don't really like to, we're kind of forced to, but we don't really like to associate the word color. Is it red or is it blue? No, it is 632 nanometers. And if you want to call it red, feel free. And if somebody else wants to call it orange, feel free. It's right on that border, but I want to call it 632 nanometers. That is its wavelength in the vacuum. End of story. And that's what we'll do. Now, we do kind of, have to fudge around that and say, hey, this is red or this is orange, but it's better just to say, hey, I don't have a green beam. I have a beam of light that has a wavelength of 550 nanometers in a vacuum. Yeah. So yeah, we can change them on all the crayons, and no more green crayons. They are 545 nanometers. Yeah. Okay, well, good, because like I said, there are two consequences I want you to see what happens when the light changes speed. And this is the fundamental physics, which is what this class is. What is the physics of it? Then we can get into the engineering of, okay, now that we can change its speed, we can control its direction, and we can build our optics, and we can build our cameras, and we can build our telescopes, and we can build our microscopes. And that's where we're headed with this, yeah.
If light left with an electromagnetic wave, would radio waves also be refracted as well? Or?
Yes. Yes, good point. Yes, and so really almost everything we say here about optics also occurs for all of our waves, our microwaves, our radio waves. Mm-hmm.
How does radio waves pass through a wall when light can't pass through a wall?
Well, okay, now, again, different colors pass through in different ways, and so it's all frequency dependent. How it interacts with this material depends on its frequency. So red is going to act a little bit different than blue. Not too much, because they're not that far apart. And that's what I'm about to show you, how even reds and blues can behave differently. You're talking about the extreme. You're going from radio waves on one end of the spectrum to light waves, and they can behave very, very different. And so where you could have a wall where light waves can't go through, radio waves could go through, which is what you would want for, a cell phone. You would still want to get your radio waves to go through the wall so that you can communicate. Yeah. Microwave window is a good example. The microwave in your kitchen. When you look inside there, you want to be able to see the food. You want light to come out of that window, but you don't want microwaves to come out of that window. And so that window lets visible light through, but not microwaves through. Yeah.
I was wondering, you said that it speeds back up once it exits.
Yeah, right.
That's kind of, I don't know, that kind of confused me.
Well,
like I was thinking about the picture of the keg that hit the grass.
Oh, yeah.
It would slow down, but then when it came out, well, that's a keg and not light, but
it was a barrel, by the way.
barrel. So.
We know where your mind is.
But the barrel wouldn't speed back up.
Okay, fair enough. And so the analogy, I agree, the analogy is not as good as it could be. See if this helps, though. If we ask ourselves why the light slows down, it's really more of an interaction with the molecule. So if you put a molecule here and a molecule here, what happens is the light continues to travel at 3 times 10 to the 8 between every atom. And what it does is it comes here, and I'll just kind of scribble and say it stops and has a little chat, and then readmits, and it's going at the speed of 3 times 10 to the 8th. And then it goes to the next atom and stops, intermingles for a while, and then goes on. And so once you realize that you run out of molecules, then it's not a surprise that it keeps going back up to the speed of light in a vacuum. It really always is going the speed of the light in the vacuum. It's just the interaction with the molecules give it a statistical average of being slower. Okay, so it's a little different than our barrel problem. Okay, but yeah.
Does it move the molecule?
If it readmits it, the net effect is no, because if here's the molecule and the light hits it, okay, you might give it some momentum and it goes this way. But then when it readmits it, it pushes it back. So the net effect is no. If it does not readmit it, if it is just pure absorption, because some are absorption, we know that when the light passes through a piece of glass like this, we know that it's not as much. I mean, there's more light going to you now than here, because some of it does get absorbed. And then, yes, some of those molecules then are moving. And that's what we call heat. That's where the energy went. The light energy went to heat, and the molecules are moving a little faster. Yeah. Well, like I said, hopefully you see 2 consequences, and one of them you just did. Let's go through the math here. And that first consequence is that the wavelength will be smaller. And we'll avoid the whole issue of saying, did the color change, by just, first of all, defining color based on frequency, not on wavelength, or better still, just never even mess with the whole idea of what color is it. We'll just define the frequency, and it stays the same. And then when we list wavelengths, we'll say, this is the wavelength when it is in a vacuum. Even though the light may actually be traveling through a piece of glass at that moment, we won't label its wavelength wavelength as the wavelength in the glass at that moment. We will label it as what is its wavelength if it was in a vacuum. But I think you can see it here. It comes back from our equation on waves. And so if we go all the way back 3, 4, 5, 6 weeks there, we had this equation between wavelength and frequency. If we replace what we've just done right there, c over n, that's the speed, then this should be the wavelength in a vacuum times the frequency divided by n. You may label this then as the wavelength in the medium, and what it would be is the wavelength in the vacuum divided by n. Your author labels it this way. He calls it lambda naught divided by n. And so one of our important equations for this chapter will be this. This is the wavelength that it will have when it's in that material here. And so this is that kind of squishing effect as it goes into the glass. Now, let's look at the second effect. And the second effect is what I kind of got started on. I kind of got off track there last time, was what if the light is not going straight in like this, but comes in at an angle? You see, right here, doesn't both the left and the right side of the beam hit the glass at the same time? But what if it was at an angle, slightly twisted? So if I change the angle a little bit, maybe I'll do it a lot so you can really see the effect. I'll stop it there. What do you notice? Yeah, and hopefully you notice where we have left last time with that barrel rolling, or with this wheel rolling, what really is a turn? A turn occurs when one side of your object is traveling at a different speed than the other side of your object. So hopefully you're not too surprised. There's nothing magical about it being light. That's why I think the author's example of a barrel, and why my example of these wheels I really like, because if they go the same speed, if each wheel has the same circumference, then both wheels go the same speed, and whether that be a fast speed or a slow speed, it doesn't matter, they will go straight. And so when you are up here before you hit the glass, and when you are down here in the glass, here the beam is going slower than here, but both sides of the beam are going the same speed. Both sides of the beam are going the same speed. So what happens here? Straight line. What happens here? Straight line. But during the transition, what happens? Yeah, one side travels a little faster than the other. And so in this case, I will make the faster side, these little wheels right here, add to circumference. But if I were to put this on, this would roll down, and then this edge is going to get a little slower. And so during that transition, there is a turn. And maybe I'm a little too close, because it doesn't look like it's turning to me. Is that? Oh yeah, yeah. So it has a bend to it, has a turn to it. And so here we have a wheel, and it turns when this side goes a little bit faster than the other. In fact, another good example, I didn't give it to you last time, but if you've ever paddled a canoe or a raft, I mean, what happens if you only paddle on one side of the canoe? You end up turning. You're so busily, and in this case, I would be paddling on my right side, and I'm always paddling on my right side. That right side goes faster, so I turn over to my left. I turn to the slower side.
So if the light's turning, if it's changing direction, it's basically turning clockwise in that picture.
Mm-hmm.
Does it not have rotational inertia of some sort?
Oh, well, it doesn't have any mass. So I'll say yes, it doesn't have any rotational inertia. This is why this was not treated with our mechanical waves of sound waves. We have no inertia here. So they're still waves. We have all those wonderful properties of waves that we learned before, but we don't have mechanical waves. We don't have inertia to worry about. Or to help, you know. Yeah.
Are we also supposed to notice that it's spread out?
Sure. I mean, it clearly would spread out too, although that's not really what I was focusing on. But yes, it would definitely spread out. And I wonder if we can see it here. I mean, I know we can see the bending, and that's really what I want to show you. And so if I do this,
Wouldn't it shrink as it comes out?
I don't know, can you see it? Looks like it's broadened a little bit in there. And it's so dim, maybe I should turn it back a little bit. Does that look a little wider in there? Of course, now when it comes out, it's going to narrow again here, so you don't see it here. But yeah, it is going to be a little bit broader.
Would that be amplitude? Since the side is frequency of the red line, then if it's wider, would it be?
No. That is not amplitude. See if we can see it a little wider in this one.
Is it related to the spreading when you narrow the hole that it was passing through?
That's a little wider. This one's terrible though. The white light can get underneath it. So that doesn't look quite as impressive as that one. Yeah, huh?
So you were saying that we can't see the change in color because we're outside the block. Why would we be able to see the change in width?
Oh!
We're seeing in the block.
Yeah, but wait, okay, fair enough. But what you're seeing in width, okay, so the beam comes here, then the beam widens up, okay? Then if it came out, it would narrow up again, right? But the stuff that narrows up is the stuff that comes this way. The stuff you are seeing is little impurities that are in this glass that then shoot some of the rays out here. That's why you actually see it. If this was a perfect piece of glass, you would never even see the beam there. I mean, the whole reason we put a little imperfections in the glass is so some of the light will actually go to you. Otherwise, we have something that looks like this through the air. And you don't see it. You don't see it till you have something to reflect off of it. So, yeah, so there's these, we call this smoked glass because we've added smoke. We've added little particles in there so you would see them. And then they would scatter off based upon the width. You would, if the light is here, you would see it go to your eyes and you would see it there. Right, and so now they come out this way perpendicular, and of course when the glass would be up here, and so when they hit the top part of the glass, then the wavelength's going to get bigger again, so the color is not going to be, the color's going to go back to what it was before, but the width is not going to go back to it. No, the width is just the physical size of where you have photons and you don't have photons. The intensity, the amplitude of it is the intensity of the light. How bright is this light?
What are we trading though? When we go from narrow to wider, what are you losing?
Oh, you are losing intensity. All of this energy that was packed here is now spread out here.
So it'd be lower.
So it'll be lower intensity and lower amplitude, if that's what you meant.
Yeah.
Yeah, okay, yeah, so this would be lower amplitude, but the width is not the amplitude.
Right.
But it would be connected because of conservation of energy, I think is what, okay, yeah, good point, yeah.
Looks like, is the width changed with the angle?
Yes, and so if we go to, I mean, if we, in fact, what makes this a little harder mathematically, okay, is how much bending. Remember this is the problem I'm after here. I'll draw it back on the board here. But here is the normal. Here comes the beam at some incident angle theta 1. I would like to know where it's going, theta 2. Unfortunately, theta 2, as you can see, is related to theta 1, doesn't it? How much bending occurs is going to be a function of how much angle did it hit. You noticed at the beginning when we went all the way back to straight up and down. There was no bending here, right? And so if we change the angle just a little bit, there's only a slight moment in time where this one gets into the block before that one. So there is some refracting, but very little. But on situations that what you're asking about, like extreme angles, then there's a lot of bending. So I wish the math was as simple as, hey, the angle changes by 5 degrees, end of story. It would make it so much easier. But it's not. How much bending occurs depends on what angle it comes into. And so you will hopefully see here the amount of bending depends on 2 factors. That's what I want you to get. The first factor is how much did its speed change? And so that's going to be the difference in those indices. And the second factor is what angle was it incidented onto that material. And you're going to see our equation here in just a second, and it'll depend on both those factors, the indexes and the angle that it came in at. Well, oh yeah.
If the light comes from the air into the glass and the speed slows down,
Yeah.
and when it comes from glass into air, will the speed increase?
Yes.
What caused that?
Okay. Again, it's not that it causes it to increase. It just, the molecules in the glass are gone, and the glass molecules are what slowed it down. See, I'll try this one again. This is what this picture was. When the light's coming in, the light is going at 3 times 10 to the 8th meters per second. Then as it goes into the glass, it stops for a moment at one molecule. Then it goes to the next, and during this time where it goes from one molecule to another, it is still going at 3 times 10 to the 8th. And then it stops at the next one, and then stops at the next one, and then stops at the next one. Eventually, it gets to the end of the glass, so there's no more stopping, and it just continues on. And then it can go its normal speed, if you will. And so it's not so much that it doesn't speed up as it isn't stopped anymore. Yeah.
Even though it goes back to the same speed, it does like permanently lose some energy, right? In the interactions that it makes.
No, and its energy is not related to its speed. Yeah. Now, when it interacts with this molecule, most of the time it re-emits the photon in the same direction. Sometimes it emits it off at a different direction. That's why we see it in here. That's why we can actually see the light as it does interfere with the little dust particles that are in there, and we can see them. And so in order for you to see anything and to observe anything, there has to be some kind of bending or moving or changing of the light. If there was no bending or moving or changing of the light, you wouldn't see anything. That's what's so neat about the air. You look over here, and I can look to the back of the room, and I can see the door. I see the door because as the light leaves the door, nothing else happens to it as it goes through the air. It's only the bending and refraction that give my brain an image. Yeah.
So the energy associated with the light is not kinetic energy.
Correct. Right. It's not kinetic energy. These don't have mass. These are not mechanical waves.
What is it?
Well, we're going to see the energy is related to its frequency. Okay. And the energy is in the photons.
So it's stored in the...
So it's stored in the field, the electromagnetic field. And so electric fields have energy in them, magnetic fields have energy in them too. Mm-hmm.
So if you were to slow light down with gravity, like if it were to just barely escape something that had a lot of gravity and then went on its way, what would cause it to speed up again after it got out of that lower speed?
Well, okay. The whole reason it slowed down is really back to space and time. Space and time is affected by the gravitational field. And so again, you would say that light travels from, say, here to here in a billionth of a second, let's say. Okay? When gravity comes around, so I'm near a black hole, then those 2 points are squished closer together. So it still takes a billionth of a second to get there. The appearance to me is light is traveling slower because those are crunched together. As I get away from the black hole, space and time now becomes like this, and now it takes a nanosecond to again do that same thing. So really, from the light's point of view, it's not doing anything different. It's still taking a billionth of a second to transverse from point 1 to point 2. It's just point 1 and point 2 are crunched together because of the black hole. Yeah.
So, in the comparison with like the barrel in the grass,
Yeah.
it's intermolecular forces that are causing the barrel to rotate.
Oh, no, yeah.
So, I mean, are there like
Let me give you an analogy and see if this helps, because I don't think I can go much further than this. But I think your argument is much deeper than that. You're saying, look, when we were rolling the barrel across here, and this edge went down here, that kind of pulled the barrel, and because the barrel was all hooked together. Okay, fair enough. And you notice when the barrel was hooked together, the barrel didn't change its length. Didn't this beam change its length? Okay, so this is not quite exactly the same as the barrel, right? But it is a little bit hooked together, and that little bit of hooked together, I would argue this way, that, okay, why would you say the barrel is hooked together? You would say the barrel is hooked together because the atoms are hooked together. Now I'd say, well, why the atoms are hooked together? Well, because there's electric forces between them. All right, where do the electric forces come from? Well, from the electric field. Okay, so what's holding the barrel together is electric field. So what's light made out of? An electric field. Right? So I would argue that the light is also held together similarly, not exactly the same. That's why you don't get exactly the same thing, but similarly, a light beam is held together. The electric field does hold it together. You don't have any molecules, you don't have any atoms, you don't have any mass, but you do have it held together. So a beam is holding itself together through the electric field.
What about air makes it not reflect light? Like, it's still atoms.
Well, it does a little bit. But okay, now let's catch this real carefully here. Here's what I really want to emphasize, okay? In fact, that's why I brought this little experiment here that I'm trying to work up to here is, look, what happens then is most of the effect on the light is going to occur when it went from one index to another, right? I mean, that's a big change to the light. And of course, it changes direction, and in this case, it spreads out, and so its intensity changes, but the direction is something you would catch with your eyes. If you were using your eyes, you would say, hey, the light bent a little bit. When light goes through the air, this is your question, as it's going through the air, the index is pretty much the same. There's no change to the light. So you don't detect anything with your eyes. You can't see it. However, since the index has to do with the number of molecules, every once in a while, or even dust, every once in a while I will see a little flash of dust in the air. I will see the sunlight scattered off of that. Or if there's mist in the air, then the sunlight will hit the mist and it will bounce off of that. And so when there's a slight change, that's mostly what I see. And well, clouds would be an excellent example because, again, they're water droplets or ice crystals even. And so there's a change in that index. I would say you probably see air visually the best when you have something that's hot, like in your car on a sunny day, and you open the door, and as the air is rushing out, that hot air has a lower density than the air on the outside. And as the sun rays come through, they will be deflected. And if you look down on the ground as the hot air is coming out, you will see shadows on the ground. That is the light being refracted because of the different indices. And the reason I pointed that one out is because this is that same idea. I mean, you can see me, right? If I put this in front of me, can you still see me? But I bet you could tell there's a piece of glass in front of my face, right? There's not much change, but there is some change, and you can see it. I bet if I held this beaker filled with these little jelly spheres, you would look at them and say, well, I can see them. And I would say you can see them because the index of these jelly spheres is about 1.3. And so the light hits them from the air, but there's a change in it. But what if these little jelly spheres are surrounded by an index that is 1.3? Right? Where are they? Trust me, they are there. Right? They haven't gone anywhere. But it's this light, this bending of the light that is going to create our images. And that's what we're getting with this. And I'll pass this around if you want to put your hand in there. Just don't grab them too hard. They are really fragile. They're just a very thin membrane of jelly and then fluffed with water so that they have the same index there. But without that change in index, you can't see the bending of the light here. And they look, as you said, almost magical, like they disappear. All right, well, I told you I would derive this equation, so let me finally get to it here. Let's then answer the question that I'm after, which is, what direction is this beam of light? Okay? And so let me draw this picture. I will put a piece of glass, not really a piece of glass, but I will say, imagine a piece of glass right there. And then here comes this laser beam. And so like this one here, maybe I'll set it up here and I'll place it something like that. Maybe I'll even turn off the chalkboard light so you can kind of see this beam. I'll put this one out of the way till we need it. But if you give some width to this beam, that's kind of this key that we've been watching for the past few moments, is that if I draw maybe the locations of the crests, you'll see that right here, that point right there gets into the glass a moment before the other side. The other side is still up there. The other side is still traveling fast, but that side is traveling slow. So which way is it going to turn? Okay, we call towards the normal here. If I were to draw a line that is perpendicular, or I could draw it here if you like, but if you can imagine it going down at an angle, my right-hand side hits the glass first, and that's going to be the slow side, so I'm going to turn in that direction. Now, I say all that because later on, and it's not really shown in this animation, but it is shown here on this glass block, what's going to happen down here. And so I guess it'll look something like this. And then what will happen? What will happen when it comes out of the glass block? Good. This edge, again, the right-hand side is going to exit the block first. And in this case, it's going where the speed is faster. And so that means my left-hand side is slower. And we're always going to turn towards that slower side. And so what will end up happening is we will speed back up. And so going in, we turn towards the normal. Going out, we turn away from the normal. And so there is hopefully what you see. And fortunately, the math is the same, whether it's going in or whether it's going out. So we just need to derive this one time, and we'll have the result we're looking for. Yeah.
So if there was just like a single stream of photons, then it wouldn't bend because the interaction between them don't turn on? Or?
No. The single stream of photons, we can say, has a width to it. And they'll bend too. Yeah. It's photon model gets a little harder to describe, but they happen too. Yeah. All right, so if I do a little geometry here, and I'm going to draw a set of triangles, and I will make a triangle. Oh, let me use black here for this triangle. And bummer, I need another color here. Well, I'll use the red since it's up here, and the red one. So the black and the red triangle for just a second here. Okay? But if we look at what we've been drawing, we called this the incident angle, theta 1. And we called this then the refracted angle, theta 2. And if we go through a couple of steps here of geometry, let me look at this angle a little better here, theta 1. If this is theta 1, then this angle right here would be what we call the complement of theta 1. It would be 90 degrees minus theta 1. And then this angle being 90 degrees means that this angle here would be theta 1 also. The reason I say that is because sine of theta 1 then would be equal to the opposite, that's this, over the hypotenuse, which would be this. Let me call this h for the hypotenuse. This, let me call it v1t. Now what do I mean by v1? v1, I mean what is the velocity of the light in that medium? And t, what is the time for the transition to occur? Because this distance that the light travels here is the transition time from the moment the first piece of light went in until the last piece of light goes in. And so what I would get is v1t over hypotenuse. Now if I do that same thing with angle number 2 down here, this down here would be theta number 2. We can go through the same argument here that, okay, if this is theta number 2, then this whole angle, well, see if I say that right, this angle here would be 90 degrees, so that this angle is rotated over the same amount that this one is rotated. So that would be theta 2. And sine theta 2 would be then this distance, which let me call it v2t. And again, what do I mean by v2? v2, I mean what is the velocity of the light in medium number 2. You see, this is the part of the light that travels while we're doing the transition. And again, t is the time during this transition. So of course what's nice about these two equations is the time is the same. The time that this one is inside of medium 2 is the same amount of time that this one is outside of medium number 1. And of course they each share the hypotenuse on their triangle, so they have the same hypotenuse. And now we have the math we need. If we rearrange this to write it as sine theta 1 over v1 equals to t over h, we can write this as sine theta 2 is equal to t over h. Since both of them equal t over h, and you know they have the same time and they have the same hypotenuse, whoops, v2, then what we get is sine theta 1 over v1 is equal to sine theta 2 over v2. Now I'm not quite done with my equation, but you begin to see how is theta 1 related to theta 2? Why? Speed difference and the angle that it hits. And that's what we were trying to argue earlier here. How much does the light bend? I wish it was an easy equation that I could say it's always the same amount. It would make our next couple of chapters really easy to do. But it's not. It's much more complicated than that. If I replace velocity in number 1 with c over its index, then the c on each side cancels off, and the compound fraction can be simplified to n1 sine theta 1 is equal to n2 sine theta 2, and I get what I was after, which is the mathematical relationship between the incident angle, and the difference in speed. So again, notice to get theta number 2, you have to know index 1 and 2, because that's important. What is the change in speed? And you need to know theta 1. Because again, how much bending occurs depends on the speed differential and the angle that it hits. And that's what this little diagram, I think, illustrated really well. And so there's our very important equation, Snell's law. Yeah.
So in lab, you pretty much left out N1. Was that for assuming that the index?
Oh, yeah, good point. For those of you who already did the lab, since you need this equation in lab, I didn't derive it for you in class. You guys today who do it in the lab, well, you just got it derived for you, so you'll be okay. But you guys who did the lab yesterday, right, we said since we are starting in air,
We're dropping out that 0.0.
call it, yeah, and we didn't go 0.03. We just dropped that off and called it 1 in lab. Yeah, yeah.
That equation is only valid if it's parallel, coming in parallel, or would it work if it like went off the edge right there?
What do you mean by off the...
The windows, as long as that's medium, as long as the medium is parallel, or would that work if, say, you pushed the light forward and it came out on the right side instead of the bottom?
Oh, so the beam hit here?
Like the
Yeah.
like the water, lab where it comes off at a different angle.
Oh, okay. So now, and maybe I'll use this as a warning, this is what makes the lab and the homework kind of complicated here, is watch what could happen. Let's say the beam comes in as you say. It's right here near the corner. Okay? I'm going to draw the normal. Now, one thing I know for sure, as it goes from air into glass, it slows down and it's going to bend towards the normal. Okay? And so that's what I had here. It's going to bend towards the normal. But in this case, I think what you're saying is now it's going to hit this surface. That's fine. Draw perpendicular. This would now be your incident angle. Call it theta 1. This now would be your index. And if it comes out, it will bend away from the normal, like that. Now that's not much bending. How about I do a little more? Bend away from the normal. So this would be theta 2. If it makes you feel better, maybe I should have labeled it as theta 1 here and theta 2 there. Then I will call this theta 3 and theta 4. So if the homework problem is saying find theta 4, I can start with this equation and go, it starts in air, 1, sine theta 1 is equal to, and then it goes into glass, let me just call it n for now, sine theta 2. But you can find, say, theta 2. And then I claim if you know theta 2, you can get theta 3. Because looking at this and assuming that this is a right-angled block here, then I know that that adds to 90 degrees. So after I did my first Snell's law here to get theta 2, I can then do a little geometry to get theta 3. Once I get theta 3, I can say n sine of theta 3 equals, and then it goes into the air, so that would be 1 times the sine of theta 4, right? And so I can get theta 4, but it's going to take Snell's law twice, one going in and one coming out, and it's also going to take a little bit of geometry to figure out what theta 3 is once I know theta 2. Right. All right, well, if that much made sense to you, let me keep going with this. Let me look at this picture from your chapter. Your author gives you a nice little graph of what we call dispersion. And now that we've had this long conversation that says, oh, the index of glass is some number, remember earlier I said that number for glass is different than water, right? Because they're different molecules. But also, aren't they slightly different for different frequencies? And so I said, you got to be careful here, because what does n really represent? N really represent how much does the light slow down? How much does the light interact? So part of the reason we have an n is because what material is it? And that makes sense why it would be different for glass and for water. But hopefully it would also make sense that it would be slightly different for different frequencies. Different vibrations would interact with those molecules slightly different. In fact, you can see a very detailed index. On the vertical axis, your author plots the index for, and let's just pick on crown glass. Because if you remember, when we looked up crown glass, it said 1.52. And that might have left you with the impression that it's 1.52 for every single color, every single frequency. But if you look closely at this graph, is it 1.2 for every color? Here are the wavelengths of the visible spectrum. Remember last time we said what are the wavelengths that the human eye can detect? What's the shortest one? Yeah, 400. What color is 400? Violet. Where's that? Laser pointer. So there's the 400. Go straight up. That's violet. What about this end of the spectrum? 700. What color? Red. Middle of the spectrum, 550 straight up is green. But look at that index for the crown glass. Is it always exactly 1.2? No. Now, notice it doesn't change by much. 1.2 is kind of that average. Notice that way over here in the large wavelengths near the reds, it goes down to 1.51. Over here in the violets, notice it goes up to 1.53. So it changes a little bit, not too much. But again, hopefully that's kind of making sense that, okay, there should be some variation, not too much, because the frequencies don't change that much between our different frequencies of visible light. But there is some change, and therefore there's some different interaction effect.
So does N crown glass continue to grow as the frequency gets larger and larger?
It's not a single function. It does a lot of this. So taking it out of the visible range too far is definitely problematic. But in this range, it does follow, and we have a lab on it, it follows a pattern that looks like this and is proportional to 1 over the square root of the wavelength. Crouchy discovered it, and then we have a lab where we actually measure the index. In fact, it might be next week, now that I think about it. I think that is next week's lab. Next week's lab is to take a prism. In fact, it looks just like, well, yours will be small. Yours will be about this big. For you guys in class, I'll use this one. Okay? But you are going to shine the light through there, and you are going to measure the bending of the different colors. And once you measure the bending, that from there will tell you what the index of refraction is, and you will have 7 colors. Well, depending on how well our equipment works. Some of you will have 7, some of you will have 10, but somewhere between 7 and 10 different colors, and you will plot that, and you will get this shape. You will get bing, 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 bing. Yeah. And so it does change. Well, I should put that word on the board. This is called dispersion. And so getting towards the end of the chapter here, what is dispersion? Dispersion is really where the index of refraction varies. It varies with wavelength. And so there's a slight variation to it. Let's see if we can see it here with some of our optics. That's why I brought out the white light here. Last time I was able to use sunlight. And unfortunately, between Tuesday and today, we have a cloud cover. Bummer. No sunlight yet. I was kind of hoping you could see it a lot easier. But do you remember on Tuesday where I took the sunlight in and I held up the prism and then it bent? Do you remember seeing all the colors up here? Well, why did different colors bend by different amounts? That's the dispersion. Right. Do you remember which one bent the most? When I held it up here, do you remember which one was closer to me? It was the violets, the blues, when the reds were further away. Now, does that make sense with this graph? What is this graph saying? What is it saying about the blues? Yeah, there's a higher index for all the blues compared to the reds. So when you shine something through your materials, on rare occasions it will be opposite, but very rare, most materials will follow this pattern, that it will be blues will have a slightly higher index than the reds. So which ones will bend the most? The blues. Let's see if we can see it here. Like I said, it's going to be a little hard to see, but I'll try it, even though we don't have, like I said, the sunlight, but I think we can see it just a little bit. And let me get something that reflects a little bit better. But if I put it right here, see how it bent the light? I don't know if you can start to see it. Can you start to see red on the top of that beam? And blue? Let me go a little bit further. And that's about as far as I'm going to get it. Can you kind of see the rainbow? Yes? No? Some of you can? Bummer. Probably you guys on that side can't see it, huh? If I kind of cover it. Yes? Anybody over there can see it? Oh, you can? Oh, good. But for those of you who can see it, which color's down here? Blue. Which one's up here? Red. And so that's my non-sunshine way of showing you that the light does bend. White light, as we said before, has all the colors in it. And so with all the colors coming in, if I can bend one color more than the other, which in the case of this glass I can, actually that one happens to be acrylic, but it's the same pattern there, and you'll see that the blues bend more and the reds a little bit less. Yeah.
So after it goes in, it changes its wavelength after it's been refracted, right?
Yeah.
Which would then cause another change as it goes further and further through the material, right? Because new wavelength and the new end, and new wavelength.
No. Once it enters, it keeps the same wavelength all the way through.
Why is that?
Well, maybe back to this picture. The only reason the wavelength changed was during the differential in speed. So if we go back to, say, well, we don't have to go back to straight up and down, but I think it's easier to see when we're straight up and down. When you're straight up and down, it's right here. It's during the transition is when the back catches up to it. Once it's inside, it keeps the same wavelength. Yeah. Now, the reason I wanted to show you dispersion is you're probably most common with dispersion in this fashion. You've probably seen this, right? A rainbow. This happens to be a double rainbow. But how does nature make a rainbow? Yeah, it's dispersion. That's exactly what it is. We know that the sunlight is got all the colors, it's got all the white light, and when it hits a raindrop, it is going to bend the light. Now, blues are going to bend more than the reds. And so a better picture of this, or at least a better scientific picture of this, would be, where's a little rain droplet here? Here's our rain droplet. Oh, that's the little one. Where's our bigger rain droplet? Here. And so you could imagine if, I was say standing here, and so I'm standing here, and let's say it's raining over there. Okay, so here's the rain droplet. Here's this little sphere made out of water. Okay? And with the sun maybe over just above, maybe like 10 o'clock in the morning, so this is our east side here, okay, and I'm looking to the west, the sunlight would come in and hit this little rain droplet, and right there, where it enters, the light is going to bend. And the blues bend more than the reds. And so you can kind of see here where it begins to spread out. The violet blends a little bit more than the red. And the green would be in between it, somewhere down in the middle here. Now then it gets to this backside and reflects. That's our last topic before we finish the chapter here. This is what we're going to call total internal reflection. So more on that in just a second. But then it comes out, and in this case, it refracts again. And again, the blue, or the violet, bending more than the reds. And so by the time it comes out, it is spread out in a fashion. And if I'm standing at just the right angle, okay, so if I'm standing at this angle here, when I look up and I see that rain droplet, what color do I see? I see the violets, right? I see the blues. And so as I stand right here, I would only see blue coming from that one rain droplet. But would I see any reds? Not from that, right, you got the idea. Not from that raindrop, but another raindrop I would. A raindrop that is higher up would come down at this angle to my eyes. And so as I stand here, I would see blues and violets coming from here. And up there, I would see reds. And in between, I would see greens. And that would be true at any angle all the way across an arch. And so that's where my rainbow would come in. I think the next picture does a little better justice of getting you the angles. Here is this person with the umbrella looking out here, and so they see violets coming from those water droplets, and they see red coming from those water droplets. The violet that came from those top water droplets doesn't get to this person, it gets to this person over here. And the red from these droplets, go down and hit the ground before his feet, so he doesn't see those. But he would see a bow, and he would see all the way around. And so you were going to see, wherever there's rain, if there's only rain on part of the sky, you only see part of a full circle. If the whole thing was raining, I guess you would, well, we're usually standing on the ground, so we usually only see half a circle. But they say the airplane pilots often see the whole circle. They're up in the sky and they see the whole rainbow. They say Hawaii is a good place to see that when you hike up and you're standing over the volcano and the big canyon. It rains every afternoon, so they say you can see that. So maybe someday I'll make it there, but I'd love to see the full circle of the rainbow. Yeah.
So is that why there's some different rainbows? Like some of them have like only reds and then, or like blues and then like they're kind of melded together at the end. Is that the ground at the end versus the wavelength? Like it's really kind of flattened out?
Oh yeah. It could be that. It also, in your case, there's a lot of other things. Remember, the rain would, for you to see this, the sky has to be filled with rain at that correct angle. And so if it's what often happens to see a rainbow, of course, you need sunlight. So you can't have a solid, cloud deck over you. Then the rain just comes down. That's when we usually get our rain. We get lots of rain, but then we don't get any sunshine. It's really after the storm front moves through that we see most of our rainbows, because then you have pockets of showers, and you need the sunlight coming in, and then you need the rain. But then they don't usually fill the whole sky, so you only see part of the rainbow. Yeah.
So what causes the doubles and the triples?
Oh, now the doubles and the triples, go back to this picture, will make more sense in a second. Yeah, he doesn't show a double, does he? I mean, he doesn't show the graphics. He shows the double up here. And notice the color order is reversed. I don't know if you caught that. But on the first rainbow, the violet is on the inside of the bow. Okay? And then it goes red to violet on the outside of the bow. And the reason the reverse and the reason for the double is back in this picture. Not that one. The other one. Is that there would be a double reflection. At a different angle, the light would come in, hit here, bounce off, hit here, bounce off, and then come out. So you're seeing a double reflection. And because the reflections are not like a mirror, you don't get 100% reflection, kind of like, you know, when you look in a piece of glass, you see a little bit of light coming from it. It's not 100% reflection. That second one's going to be really, really dim. So the chances of seeing a second one require you to have some significantly bright sunlight. The barrier between the water and the air. See how this is showing the light coming in and bouncing off the. See, now they don't. Well, here's this. I don't know. Can you? If I angle it, can you see those lights? So you get some reflection, right? There is a small amount of light that is reflected off of here. And so anytime there's a barrier, anytime there's and in this case, water to air, there's a reflection. So when there's a change in index, there's going to be a little reflection. Oh, either a little to a lot, and that's our last topic here. There could be a lot. It could be 100% if it's what we call total internal reflection.
You're saying it's reflecting off of the raindrops?
Yeah, the backside of the raindrop.
Causing the double?
Yeah. So the picture would look like this. Bounce, bounce, and out. So there's, no, the first rainbow is that, one reflection. Second rainbow.
I have a source from two different locations.
No, okay, no, it's a different, okay, so the sun is at, there's only one sun, right? Okay, so the first rainbow does this. The second rainbow does that. So you see the second rainbow higher up than the first rainbow. Now, each of these are making a second rainbow and a first rainbow. They're just not going to you. So you see this light from this one, and you call that the first rainbow. You see the light from that one up above it, that's your second rainbow. Okay. Well, like I said here, I need to talk about this last piece of this puzzle, and that's that reflection off this backside. Watch this for a moment. I think you begin to see it before. If I turned out the lights, this is the part you're asking about here. Maybe I'll start with the white light here. But when I turn this, I want you to notice something. I turned it, and I got it to here so you could see the colors. What happens if I turn it even more, like that? Do you see that difference? Do you see that right here, that beam of light is trying to go what I would call parallel to the surface. And instead of going parallel, it actually reflects back. Now, of course, why is that? Well, see if this picture makes any sense. It fits in with what we did at the beginning, which was, the following, that the light would bend. But this is really just an extreme refraction, if you will. We call it a total internal reflection because here all the light is reflected. But let me draw this picture again. Let me draw this as being air. this as being glass, let me draw a normal. And let me ask you this. If the light comes in and hits the surface, which way will it bend? Towards the normal. Okay. But here's the real key to it. What about this one? Which way will it bend? Away from the normal. Now, the reason I say this is the key one here is because it can only occur here. It can occur here, but watch this. What if I already have my beam of light in the glass, and it's coming in like this? And let me give some width to it. Here's some width. And let's say that it bends it so much that it wanted to travel perpendicular here. And when I say perpendicular, I guess I mean this. I should mean parallel to the surface. Can the light do this? What problem do you have there? Yeah, one side is in the glass and one side is outside of the glass. Well, that's not going to happen, because what will happen if one side's outside, it's going to go faster, right? So what will happen is it will arch around, and then go back in. And so the picture I'm trying to get you to see here is that if I start with a piece of glass, and let me emphasize, you have to be in the glass because you have to bend away from the normal. This could never occur if you're bending towards the normal, right? If you're bending towards the normal, well, then you'll never get a situation where half the beam is out of the index and half of it is in the index. But if you are already in the piece of glass and your angle comes in like this, and you bend away from the normal, and then you turn it a little more and you bend even further away from the normal, there is some magical point, which we are going to call the critical angle, that when you get to that point, kind of looking at this, you would have the beam. If I give some width to this, you're going to have the outside of the beam arch around before this point can get out, and that beam is going to head back up. And that would be true for any angle greater than that. I mean, this right here is what we're going to call the critical angle, but it would be true for any angle greater than that. In fact, for greater angles, it's even easier to see, I think. If here is the index, and we are at some enormously large angle, when this side gets out, it just has to arch a little bit before this will speed around and go back. So again, I want to emphasize that there are certain cases where the light can actually act more like a reflection than a refraction because it bends around so much. And that's what this raindrop is doing. This raindrop is actually hitting over here at an angle that is greater than the critical angle, and as such it reflects all the light back down. Whereas the double rainbow, the angle is less than the critical angle, so some light comes out, only a fraction of it reflects back down, and the second rainbow is going to be a lot dimmer. And it's also going to be reversed ordered because it has a reflection, just like you standing in front of a mirror. If you ever stand in front of a mirror, and if you lift your right hand, what happens to your image? It lifts its left hand, right? Your left and right are reversed. And so that's that second reflection and why the colors are reversed on the double rainbow. But like I said, this is called total internal reflection. See if we can see it. I think you can see it a little bit better with the laser beam. Let me turn this one off. and come back here to this laser beam here, if I put a triangle up here, hopefully you'll see the light bends towards the normal going into the triangle. Then it bends away from the normal. And if I keep going, keep going, keep going, keep going, keep going, keep going. Oh, getting close. Keep going. Still some's coming out, right? Keep going right there. And so on this surface right there, I would say I have total internal reflection. All the light is trapped inside. So again, I want to emphasize, going into the glass is not total internal reflection. It's got to be coming out of the glass. You have to go from a slow medium to a fast medium for this to work. But there are certain situations like this one where you would get all the light reflected. Of course, in this case, it then comes out right here. So, but less than that, the light comes out. More than that, the light doesn't come out. Now, hopefully this will remind you of modern technology. Here is our fiber optics. Here is our old computer network putting our relay to our computer. And between these are some fibers. I'll pass them around here in just a second, but I want to shine the laser and the light through them first. Here is my homegrown fiber. It's not a very good fiber, but that's probably good because it illustrates it really well. In fact, I'll start with one before I heated it up. If I just turn on a little flashlight and put the end of it, the light will go down my fiber. Now, the fact that you can see the light is a bad sign, right? What does that mean? Yeah, that means there are impurities in it and they are reflecting the light back to you. So this wouldn't make a good fiber because after a couple miles of this, there would be no more light left in it. But it makes a good teaching tool because you can see the light. But look at the end of it. The end of it is where most of the light ends up going because it has gone through this fiber, something that looks like this. And the light beam hits and hits and hits and hits and hits. And as long as it is at an angle at or greater than the critical angle, that light is now trapped inside of that fiber. Now, what does that mean? That means I can actually bend the fiber. As long as I don't bend it too much. I can change this picture to look something like this. What if my fiber has a bend to it? Well, as long as it's not bent too much, that light can still be trapped inside. And you can kind of see it here. This is bent a little too much, but I think it illustrates it well. Do you see light coming out that end? Yeah. And so it goes down, it goes around the curve. You can see right here I bent it quite a bit. We're losing a lot of light right there. Okay? So there's a lot of light that is less than the critical angle there. But there still apparently is a lot of light still at or greater than the critical angle because it will go through that pipe and come out this end. And so like I said, that's my cheapy fiber optics. My real fiber optics, I'm kind of hoping you can see. Let's see, can you see any light there? Is it dark enough in the room there? Maybe I'll hold it because I want to. If I move the light back and forth, can you see it flash at all in there? Yeah. Sort of. All right. Hold it out. Yeah, you see a flash? And so there are little tiny fibers, and then they're only the size of about a human hair, so it's going to be hard to see from this distance. That's why I'm going to pass it out, see if you want to play with it. Here's another one, too. Here's one that the fibers, you can kind of see the light at the end of the fibers there. as it kind of comes to the end.
Fiber optic, though.
Huh?
There used to be a toy with one fiber optics, actually.
A toy, what?
There's a toy of some sort. Basically, it's more of a decorative tabletop toy. Basically, it's just a bunch of like fibers sticking out like a little flower thing.
Oh, yeah, I have seen those in stores. Yeah, I've been tempted to buy one, but I guess I thought I wasn't that. But you're right. They just got a bunch of fibers and they fan out like a bouquet of flowers. And then the light underneath it makes them come out to the end. So I'll pass this around if you guys want to play with it or send it on further down. I don't know. Here's the light, and you can look at it. But it's like I said, I think it does a good job of illustrating our fibers. But let me give you some calculations here on what would that angle be then. How would we calculate or find that particular angle? Yeah, and hopefully you see it right here. I'll redraw this picture. But if you remember, the key to the discussion was that the beam that is coming to the outside needs to be heading parallel to the surface. So if I put, say, index N1 going into index number 2, then what will happen here is as the light comes in, it will bend and go parallel to the surface. Now please remember, this would only occur if N2 is less than N1, right? We have to be going into a faster moving surface to bend away from the normal. So the whole idea of a critical angle only makes sense when you're talking about from in the glass to out, not out of the glass in. Okay, you've got to be going into a faster medium because it's got to bend away from the normal. So with that said, this would be what I would call the critical angle. What is the critical angle needed to make the secondary beam be at 90 degrees? So when we apply Snell's law, we would go N1 sine of the critical angle would equal to N2 times the sine of 90 degrees. Sine of 90 is 1. It's 1, right? So sine of the critical angle would be N2 over N1. And so there would be our critical angle. And just in case I didn't emphasize this enough, let me emphasize it because this is modern world of technology. These little pulses of light are the data and the information that you guys are constantly getting when you're on the phone or the internet here, and these pulses of light. And in our area, there is a main backbone of all of the southwest United States here. And that thing backbone goes right up our train tracks right here. I mean, you could just walk down campus and buried right next to that train track is all the data from San Diego, Los Angeles, and Phoenix. And it is just flying across that network, trying to get to Morro Bay because it goes down there and it goes underwater and goes all the way to Hawaii from there. But that's the main AT&T line. So don't... Fortunately, one human hair size can handle 10 to 15 gigabytes of information.
So what do we use?
Oh, I don't know. That's a very good question. What is all of Southern California use? Well, I've seen the container that the fiber's in. It's a metal pipe about this big, so it can't be any bigger than that. But I don't know how many fibers are in there.
Gigabits.
And gigabits, yeah, what did I say?
Speed is measured in bits.
Oh, what did I say?
Storage is measured in bytes.
Oh, gigabits, yeah, gigabits, yeah.
How in the world can you translate information into light? Is it like does light come in pulses like on off like in like binary?
Yeah. So this is how you code the information going down the fiber. You send a laser and you go on off on off 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 on on off 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 on off, and you can get a lot of information if you do that 10 billion times a second, right? And so there's our whole world and our data. All right, well, that's the end of the chapter. I wanted to make sure we had a little time to do some examples. Oh, good, we do. And so, as I mentioned, I think most of what you will find in this chapter is either the law of reflection or Snell's law, and then a lot of geometry to go with it. Right? So, I have on my list here number 43 to get us started, but I'll might end up jumping to the harder one before we get too far along here, so we can at least see the harder one. I did want to show you, well, we'll see if we kind of get that far here. But what I say, number 43? 43. I'll leave that there in case we get to the hard one real soon. And it has a nice diagram. But this first one is simply a Snell's law and says, all right, let's go ahead and do this. It says, '43 here. A narrow beam of light is incident from air onto a surface of glass which has an index of 1.56. Find the angle of incidence for which the corresponding angle of refraction is half. All right? So they've left it a little harder for me. I guess that's why it's a blue one here, to say, all right, if this is the beam coming in, theta 1, then as it goes from air into glass, and then give me the index for the glass, it will bend, and I'll start by asking you which way? Towards the normal. So it will be now heading off in that direction, theta 2. And the question they're asking here is, what angle is that such that the refracted angle is half? And as I mentioned about an hour ago or so, the whole point of this chapter is really learning how do we control light. And we got that answer now. We can control it by either reflections or refractions. And included in that refraction is dispersion and total internal reflection. But once we know how to control this light, we can build things like fiber optics, we can build things like telescopes, we can build things like microscopes, we can build things like glasses to correct vision problems. And there's all kinds of things we can do now that we can control the light. But in this case, it is saying theta 2 is equal to 1/2 of theta 1. Right? And so there is my first step, if you will. Now, if I apply Snell's law says n1 sine theta 1 is equal to n2 sine theta 2. As I put this in, the light is coming from the air, so that's a 1. That is sine of theta 1. It's going where? Well, it's going into the glass, 1.52. And it would be then the sine of theta 2, which we're debating if I should put that into theta 1 or theta 2. What are we looking for here? It says find the angle of incidence. So I am looking for theta 1. But I think this would actually be easier for you guys to see mathematically if I write it as theta 2. So let me do that for a moment. So theta 1 is twice theta 2. And then this is theta 2. And the reason I picked that is because hopefully this stands out to you, right? And that's part of the reason I picked this. Of course, obviously part of it is just Snell's law, but the other part is we got to remember our trig identities. We got to remember our geometry. That's kind of where some of the troubles begin when in doing the homework. And so you might recognize this one. What's this one? Yeah, 2 sine theta 2 times cosine theta 2. And maybe I should double check. I'm pretty sure that's right. But where would I find it? Yeah, good. I heard both answers. Somebody said Appendix B, and that's what I was getting at. Another of you said Google. Okay, that's fine too. All right. But there's your trig identity. And then fortunately, now the problem becomes pretty easy. But like I said, I wanted to illustrate Snell's law and some of your trig identities. So that would cancel off. So now I can get cosine of theta 2 equals, and we get 1.56 divided by 2. So now a little calculator work, and I can get the refracted angle, and then I'll get the reflected angle. So 1.56 divided by 2, inverse of the cosine. Oh, and I better check what mode I'm in. Okay, I'm in degrees. All right, so that would be 38 degrees, 38.7. So that means theta 1 would be twice that. And so an incident angle at about 77.5 is then bent and comes out at about a 38.7. Okay. Well, I'll take this moment to kind of pass this around here. Some of the questions you have on the homework that throws students off are the bending of the light. Look carefully at this. It's 2 beakers, 2 pennies. At the bottom, the only difference is one has water in it. Okay? But I want you to look at them. Put them in front of you. Put them on the table. Take a look at them. The penny underwater is going to look a little bit closer to you. Why? Both. It'll look closer and bigger, yeah. But I'm going with the closer. Yeah. This will kind of set us up for the homework as well as next chapter. Your author illustrates it, I think, well in this picture with a fish. I don't have a fish, I got a penny here, but same idea here. Let's take a look at what is this fish going to see. Now they show the light coming into the fish, but does the light travel in a straight line going to the fish? No, it's some bending. And so that's what you're going to see in this beaker. You're going to see this beaker, one is filled with water, one is not filled with water. The one that's not filled with water, let me talk about it first. Here's the penny. And what's going to happen is one beam of light is going to go up and go into your left eye. Another little beam will go up and go into your right eye. And so you will use your 2 eyes, and in case you don't know, and this is going to set us up for next chapter, is why do you have 2 eyes? It's a depth perception. It's the way you tell how far something is away. The angle of the light that is slightly different in the left eye compared to a right eye will give you a perspective of how far something away is. So the way you see this penny here is that you realize the light going to your left eye and the light going to your right eye traveled in a straight line, and as it came to a straight line, and the angle that your eyes are adjusted will tell you how deep is the penny. But what would happen if that penny is underwater? Or in the case of this fish is trying to grab an insect that is flying around on top of the water. I'll exaggerate here, but if you look at the light that comes up from the penny, it will bend which way? Away from the normal, right? We're going from water, where the light is slow, to air, where the light is fast. And so this beam which goes to your left eye and this beam which goes to your right eye, your brain now traces back and says, oh, there's the penny. Is that really where the light was coming from? No. But your brain has been programmed that you think of light as traveling in a straight line. And so your the light has been disturbed, if you will. Your perspective is off. And so the same thing with this crazy fish. This crazy fish will hopefully learn right away that the insect is actually right there. If the fish forgets that the light bent, the fish will probably jump right about there for the insect. Miss it, starve to death because of its stupidity, and we don't have to worry about its offsprings having the same problems, right? And so there's your evolution in process here. But because of the bending of that light, that fish has learned where the insect is. It's not in a straight line directly above it. The reverse is true, I guess, for the baby bear. The baby bear who sees the fish in the water is not going to swat where you look straight at the fish, but realize that if I'm looking at the fish is actually back here a little bit. And so there's where I reach for the fish. And same idea, there is going to be some bending of that light. And so watch the problems as you do that. We got, like I said, some trickier ones like that. In fact, let's look at problem number, they got a good diagram of this, 51. 51. But something's weird on my diagrams here. I don't know if I have all the problems listed. I must not have downloaded all the graphics. But I think I have 51, 49, 51. Good, I do. Oops, that's the thumbnail again. Let's look at this one together. And again, hopefully we'll illustrate the same thing. Is what you're going to do in this beginning chapter is either law of reflection or Snell's law with some geometry and some trigonometry to figure out what are angles. Okay? And so let's take a look at this one. 51 says this. A light beam in figure 51 strikes surface number 2 at its critical angle. What is the incident angle theta 1? Okay, now they gave me some very important information. Here's that beam. All right. So the ultimate question is this. What is the incident angle? What is theta 1? And so we have this, what looks like glass. I don't really know what it is. They don't say. But they do say that it comes in and it hits at a critical angle. Now that tells me a lot of very important pieces of information. 3 in particular. First of all, if this is a critical angle, what do we know about the speed out here compared to here?
Faster?
It's faster. So what do we know about the bending here? Towards the normal or away from the normal? Right. So one of the first things that goes on to my mind, now fortunately they've given me a drawing, so I didn't have to draw it, but if I had to draw this, I would have to decide, am I going to draw the beam towards the normal or away from the normal? And the fact that they said it was critical angle is telling me that this is a slower speed than this one. This is a higher index than this one. This one is bending towards the normal. So that's the first thing that goes on. Second thing, since I said it was a critical angle, then this beam that would come out doesn't really come out. You can draw it parallel if you want to kind of remind you that what's going to happen to this beam. It's going to go this way. It's going to be a reflection. And they've helped me out, 42 and 42. They probably should have just given me one and made me realize, wait a minute, if this is a reflection now, the law of reflection says that's got to be a 42 and that's got to be a 42.
Well, considering that they give us, the critical angle, I think we can choose kind of proportion between n1 and n2.
And I can find n, can I?
The proportion between the two.
Well, let's see. What did we learn about the critical angle? Well, the critical angle is when this angle coming out is 90 degrees. And what they are telling me when I apply the critical angle, when I apply Snell's law right here at this surface, not this one yet. I'm going to come back to that one. And that's what I wanted to illustrate. Some of these problems get pretty long because you've got to apply Snell's law at every little surface, and you've got to do some geometry between surface to surface as the beams go through here. But I would start right here and say that angle is 42. So the angle coming in is 42 degrees. That is Snell's law. The angle coming out is 90 degrees. That's what they meant by critical angle. This then would be n, the index of whatever that triangle is made out of. Now this one, what it goes into, I think do they say air? A beam of light strikes surface number 2 at a critical angle. So I guess they don't really say we're in air. So maybe I better put a theta 1 and an N1 and an N2. I thought they had said air, but you're right then. I can't actually find the index, but I can find the ratio of the index. Yeah.
What is the apex angle?
Apex angle? Oh, that's the corner of the triangle. So the angle is 60 degrees here. The apex angle is 60 degrees. And in this case, it looks like they're trying to draw me an equilateral triangle, but I don't know. And it turns out I won't need to know whether those are 60 or not, but I will need to know this one. Yeah. Well, as I write this out then, I'll just write it as N2 over N1 is equal to, and so I'll start there. There's my first calculation, the sine of 42 degrees. So this is 0.669. Okay? Now, let me be careful what I mean here by N1 and N2, because this could throw me off. What is N1? When I did this problem, yeah, that is the inside piece. So I would prefer to write this really as inside and outside, as opposed to N1 and N2. Because again, I'm going to use Snell's law, but I'm going to use Snell's law at the upper part. And N1 is what it is going into, so that'll be the outside. Oh, did I get them backwards?
Yeah, N1 is
yeah. Okay, so this is outside, yes, thank you. And this is inside. Yeah, good. And that's less than 1. That should make sense, because outside we said was less than inside. That's how we got our angle price. So there would be my first step. Okay? But now let's do a little bit of drawing here. Knowing that information, and knowing this is 42, and knowing this is 60, I bet I can get this angle right there. Right? Now I got to do a little geometry. Okay? And this beam coming down, something like this, hits, reflects off, and what I know is that is 42. So what's this one? Okay? So it's complement, right? 48? Now they show me in the picture that this is 60. So what's this one? Does that come out to be 72? 100, 108, 100, yeah, 72. So what's this one? 18, right? And again, in case I went too fast with the geometry, remember these add up to be 90 degrees. The sum of the angles in a triangle add up to 180. And again, these two add up to 90 degrees. So that means I should be able to apply Snell's law there. And so let me do Snell's law again. And I will apply Snell's law for the first surface. And so this will be N1 sine theta 1 is equal to N2 sine theta 2. But again, let me be careful with what I mean by 1 and 2, because 1 is outside. Okay, and so that's where the light is starting. The light is starting on the outside, going inside. That's the opposite of what we did on the second surface here. And so N2 is the inside. And then this would be the sine of the refracted angle. But that's what I went through, and I found that that refracted angle is 18 degrees. So the sine of theta 1 would be the ratio of the inside index over the outside index times the sine of 18 degrees. And so again, going to have to do a little bit of calculator work, but of course my point here was to illustrate you between Snell's law geometry and some trigonometry identities. That's what our problems are going to be like for this chapter here. And so it looks like this is the reciprocal of that.
Why did we swap N1 and N2? Why not be consistent?
Snell's law means N1 is where the light starts, N2 is where the light ends. Okay?
Why do we
Not sure. What you mean? Could we switch 1 and 2?
I mean, we could just call N1 the index of the inside and N2 the index of the outside. The equation will still work.
Oh, if you. Okay. Yeah. Yeah.
We don't have to follow what Snell did.
No, we don't have to follow what Snell's do, but I'm worried if we don't, we're going to get into troubles later on. But so I'm going to put it this way. Particularly if this triangle was buried underwater. So we had air up here, and then glass, and then water. I need to be real careful about what index is it starting in, going into, starting in, going into.
I would just call it N1, 2, and 3 in that case.
Right. And so when you write down Snell's law, which is written as a 2 and a 3, I mean a 1 and a 2, where does the 3 go?
Well, you have
Okay,
one equation
you got
with
it.
1 and 2, and then
Fair
another
enough.
equation with 2 and 3.
Fair enough. And that's essentially what I'm doing. I'm just calling it inside and outside. Yeah. All right, so now if I grab my calculator here, this, I guess, is the reciprocal, 0.669 reciprocal times sine of 18 degrees, inverse sine of that answer, and I've got 27.5 degrees for the incident angle. So for this angle, this would come in, nice incident angle, bounces off, comes around, and sure enough. Well, let me show you one more thing that will help you, I think, in terms of the terminology here. Let me turn the lights down here a little bit again, because there'll be a couple of questions that you'll come across the homework, and they'll say, find the deviation angle. What? What's the deviation angle? Well, let me take away this triangle for a moment. Right now, this beam is headed in that direction. The deviation angle is, where is it headed now? That is what we're going to refer to as the deviation angle. What angle was it going without that glass piece or that acrylic or whatever you put there? And now, where is it going compared to when you put there? So what is that deviation angle? So be on your lookout for that. And then you'll see this other word, minimum deviation angle. Well, again, watch carefully in this picture. I'll kind of erase this. I'll move the glass block. So that little beam right there, that's where the beam is going, right? If I put my prism there, it bends it, that's the deviation angle. Watch what happens when I rotate the prism. If I rotate it this way, the beam actually went up for a second, then what would you say about the deviation angle? Increasing or decreasing? Yeah. So now it is increasing. I am getting away from the minimum deviation angle. In other words, depending on how you set your triangle up here, you can have different deviation angles. But there's only one minimum deviation angle. Watch this. If I rotate this, it gets closer and closer and closer. So we're getting closer to the minimum. That's about the minimum, because watch what happens when I keep rotating. What do you notice now? Deviation angles start to increase. So there is only one place where that beam gets as close as it can back to where it was going before. That is the minimum deviation angle. So when they ask you to find the minimum deviation angle, they're also really telling you, adjust your prism at whatever the correct angle is to get the minimum. And there's some fun math right there. Find the minimum of a function. Yeah.
Would that happen when the incident angles are equal?
No.
No.
No. It acts. No. It's going to happen when the light beam going through the triangle is parallel to the base. And that's what you're asked to show. Yeah, no homework problem. All right, well, I'll leave it there for today. I think we're a minute or two done, so you can go home and tell everybody how easy this class is. We get out early, and you're going to want to take it next year, I know.